In our lesson 1.9, we're now on objective 3, which is changing dimensions. And again, like I said, you're gonna need to do more than just. Sometimes you're gonna feel like it's just so easy, Mrs. Grant. If you double it, everything doubles. If you triple it, everything triples. If you take it in half, everything is in half. But guess what? It's not that easy. We have to think hard. We have to do more thinking than that. So if we are given here, first of all, a two-dimensional object figure, which is a rectangle. We have rectangle A, and it's been multiplied by 2. Every dimension of it has been multiplied by 2 to form rectangle B. So the first thing we're going to fill out here is number 1. What are the new dimensions of rectangle B? So if we double the side lengths, what are the new dimensions? What are the dimensions, first of all, of rectangle A? John?
6 centimeters, and the length is 6 centimeters, and the width is 2 centimeters.
Yeah, so it's a 6 centimeter by 2 centimeter rectangle. What will its new dimensions be after we multiply it by 2? Allison?
12 centimeters by 4 centimeters.
So now it's going to be 12 centimeters, and by, you can use the x here. This is okay if you use the x here. By what? What was the other one? 4 centimeters. Okay. So the new dimensions are 12 centimeters by 4 centimeters. Okay, what's the ratio of the corresponding sides? John, what do you think?
6, 12, 2, 4.
Okay, so 6 over 12?
Or no, it'd be 2 over 6 and then 4 over 12. Wouldn't that?
I just want a ratio of corresponding sides. So tell me
sorry,
what sides even correspond. Patience?
6 over 12 and then 2 over 4.
Okay, well, let's think of it like that. What if we put 6 over 12? What is 6 over 12 simplified?
1/2.
1/2. Is the bigger rectangle half as big as the original one?
No.
No, it's double, shouldn't it be? So we got to just switch our ratio up. And we always put on top the new measure. So let's go with 12 centimeters over how many? 6 centimeters. And that comparison is actually 2, isn't it? Or we could do, what if we compare the widths? Well, the new width is 4. The old width is 2. And that also equals 2. So the thing that's tricky here is, and students have a really hard time understanding what this means, ratio of corresponding sides. Can you think of another mathematical term that really means the same thing? If we multiplied by 2, what's that 2 really also known as? A scale factor. It's really just a scale factor. So let's just put that here. When they ask you for this ratio of corresponding sides, they're really just asking you for the scale factor. So in this case, everything, the dimensions were doubled, so the scale factor is 2, so that's also known as our ratio of corresponding sides. Every dimension got 2 times larger. Okay, well, let's complete the table and see what that does to by using a scale factor of 2, or the ratio of corresponding sides being 2, what does that do to the perimeter of those rectangles, and what does it do to the area? So let's just do perimeter first. How do you find the perimeter of a rectangle? How do you find the perimeter of a rectangle, John?
The length plus width plus width.
So
L2
L
plus W2.
Yeah, so there's 2 lengths that are the same, and there are 2 widths that are the same, and perimeter means the distance around. So we have to add all of those lengths. So the perimeter of our rectangle A would be 2 times, the length is 6, plus 2 times the width, which is 2. So what's 2 times 6?
12.
12, and 2 times 2? 4, so 12 plus 4 is 16, so the perimeter is 16, and that's 16 what, by the way? Centimeters. There's still centimeters. When you add centimeters to centimeters, you still have centimeters when you're all done, right? Okay, let's find the perimeter of rectangle B now. So rectangle B has 2 lengths of 12 plus 2 widths of 4. twelves is
24.
24, and 2 eights is
There are 2 4s.
8, and 24 plus 8 is 32. So 32 centimeters is the perimeter of our larger rectangle, our enlarged one. Okay, we're just going to leave the area thing alone for a little bit, and we're going to jump down to 4 and 5. So what is the ratio of the perimeters? So we're going to put, no, remember the new one goes on top, so 32 over 16. We can leave the labels out, it's okay. 32 over 16, what does that simplify to?
2.
2, yeah, that is 2. So if you double the dimensions, what happens to the perimeter? It also doubles, doesn't it? If you double the dimensions, the perimeter doubles also. Because that's what we took the perimeter of the new one, divided it by the perimeter of the old one, and we got 2, so it doubled, didn't it? So how is the ratio of the perimeters related to the ratio of the corresponding sides? What would you say? Here, we kind of like to make a little summary note here. John?
They all have a scale factor of 2.
Okay, so the ratio of the corresponding sides is the same as the ratio of the perimeters, or since they're asking about the perimeters, let's start there. The ratio of the perimeters is the same as, right, is the same as the ratio of the corresponding sides. But can we make that a lot shorter? What if we say ratio of corresponding sides really is scale factor? So let's just say same as the scale factor, okay? Because that's what ratio of corresponding sides is really just the scale factor. So you double the side lengths, you end up double the perimeter. What would happen if we tripled the side lengths then? You triple the perimeter. What if we made the dimensions 1/4 the size they were to start with? What would happen to the perimeter? It'd be 1/4 as much too. So the ratio of the perimeters is the same as the scale factors. Okay, let's go back up to area now. Let's find the area of these two rectangles. How do we find area of a rectangle, first of all?
Length times width.
Length times width. Okay, so length times width. So this one will be 6 times 2, which is 12. What's the label on this one?
Centimeters squared.
Centimeters squared. Two-dimensional, we found, we took a dimension times a dimension, that's squared. And then this one is 12 times 4, which is 48, and those also are centimeters squared. What does area mean, really? I mean, that's the formula for what does area really mean? We know that perimeter means the distance around. What does area really mean?
The total space that it takes up, or like the total inside and space.
Yeah, there's no space that a two-dimensional object takes up, by the way, right? The floor of this room is a two-dimensional. It's a rectangle.
Area that it covers. Right?
So area means how many squares can you put on it? How many squares does it take to cover it that are whatever it's measured in? This one's measured in centimeters. So it would take 48 centimeter by centimeter squares to cover that larger rectangle. It would take 12 little centimeter squares to cover the other rectangle. To cover it, just lay on top of it and cover it all up. Okay, well then let's go down here and find out what's the ratio of the areas. Shelby?
48 centimeters squared over 12 centimeters squared.
So 48 over 12, and 48 over 12 is equal to 4. So if you double the dimensions of a rectangle, the area does what? Quadruples. So, I wonder if we could maybe think about what's another way multiplying we can get 4. We double the dimensions. 2 times what is 4?
2 times 2.
2 times itself. Yeah. So if you double the dimensions, you're going to get 2 times itself for the area. For the area is going to get that many times bigger. So we're going to say that the ratio of the areas is the square. That means take a number times itself. That's what square means. Take a number times itself. So the ratio of the areas is the square of the scale factor. Let's check this out. How about if we triple the sidelines? What's 2 times 3? 6. What's 6 times 3? 18. Okay. So our scale factor is 3, right? Ratio of corresponding sides is 3. Okay, what do you think the ratio of the areas is going to be then?
6.
6? Is that the square of
9.
No, 9.
9.
9.
Should be 9, shouldn't it? The square of the scale factor? Because 3 squared is 9. Well, let's check it out and see if it works. 6 times 2 is 12. 6 times 18?
No.
108. Ratio of their areas, 108 to 12. How many times does 12 go into 108? 6 times? 9 times. So the square of the scale factor, not times 2 times the scale factor times itself. So what if we quadruple the dimensions? What would happen to the area?
It would be
How many times bigger would it get?
8 times.
16 times bigger, because 4 times 4 is 16. It is 16. So let me show you even up here, just kind of, they're not really drawn to scale, but let's look at this, 2 by 6. In reality, we're supposed to get 4 of these in there. Doesn't it really look like we could get 4 in there? So in this one, we should be able to get how many of these on top of this? 9 of them, right? We should be able to get 9 of them. Okay, and if you do some playing around, some drawing of your own, you'll start catching on to this. Okay, now let's work with 3-dimensional. We got a rectangular prism here, rectangular prism A and rectangular prism B. We're going to double the dimensions of A to get B. So what will the new dimensions be for prism B? 5 doubled is? 10. So 10 inches. So 10 by 6 doubled is 12 inches. And the height, 3 inches, is going to get doubled to 6 inches, right? Okay. So there's our new prism. Its dimensions are 10 by 12 by 6. Okay, what's the ratio of the corresponding sides? 2. We doubled everything, right? 2. Okay. And if you don't believe me, try it. 10 over 5 is? 12 over 6 is? 6 over 3 is? Oh, okay, so we've got it, right? The scale factor is 2. Okay, what's the volume of prism A? Does anybody happen to know how to find the volume of a rectangular prism? Dylan, what do you do?
Length times width times height.
Length times width times height. So for prism A, we have to take 5 times 6 times 3, which is, Allison? 90. 90 what? Inches cubed. 3-dimensional. We took 3 inches. We took inch times inch times inch. That's inches cubed. Okay, what's the volume of prism B? Well, it's going to be 10 times 12 times 6. Oh, we can all do this. No calculator needed. 10 times 12 is? 120. 120 times 6 is?
700.
720. Ooh, got a lot bigger. Well, let's figure out the ratio of the volumes then. What are we going to set up for our ratio?
720 over 90.
720 over 90. And we will divide that out and we will get, John? 8. So the ratio of the volumes is 8. How is the ratio of the volumes then related to the ratio of the corresponding sides? Remember, the ratio of the corresponding sides is 2, and the ratio of the volumes is 8. So what do you think the relationship is here? What do you think we can count on? Shelby?
8 cubed. Like 2 cubed.
Yeah, 2 cubed. 2 times 2 is
4.
4 times 2 again is
8.
8. Yeah, so we would say the ratio of the volumes is the cube of the scale factor. So tell me then, if we would have tripled the dimensions, what would have happened to the volume? It would have been 27 times bigger. 3, 3, 3. 3 times 3 is? Times 3 is? 27. It would have gotten 27 times bigger. Okay. So that's just kind of like a summary of what we can always count on. The ratio of the corresponding sides and the perimeters ratio, how are they related? The ratio of the scale factor and the ratio of the perimeters is the same. The ratio of the corresponding sides, the scale factor, and the area, the square of the scale factor. The scale factor times itself. Area, length times width. Scale factor times itself. And the ratio of the corresponding sides compared to the ratio of the volumes. The scale factor compared to the ratio of the volumes. What happens? It's the cube of the scale factor. If you triple all 3 dimensions, then 3 times 3 times 3, you cube the scale factor. Okay, let's go back then now and use those. No pictures now. We have no pictures, we have to go without our pictures. So let's just move that down for a bit. Okay, a rectangle has a width of 3 inches and a length of 12 inches. Now, feel free in your homework if this helps you to draw it, but we're going to try and do it without drawing it. Every dimension of the rectangle is multiplied by 1/3 to form a similar rectangle. How would the ratio of the perimeters compare to the ratio of the corresponding sides? Do you think we need to go through all the work of finding both of those perimeters? Why not? What did we say on the front side?
You can just find the ratio of the first 2 and square that.
Wait a minute, how does the ratio of the corresponding sides compare to the ratio of the perimeters?
They're
They're
the same.
the same.
Oh wait, yeah.
And the ratio of the corresponding sides is really the what? Okay, what's the scale factor in this problem?
1/3.
1/3. Here's our scale factor right here. Multiplied by 1/3. So the ratio of the perimeters is going to be what?
The same
The same
as.
as that, isn't it?
Yeah.
So the ratio of the perimeters. We don't even have to find those perimeters. We just know that the ratio of their perimeters will be 1/3. 1/3, the same as the scale factor. You take the dimensions times 1/3, you just cut the perimeter to 1/3 of what it was. Okay, well then, now they want us to say, how would the ratio of the areas compare then? So in other words, what would the ratio of the areas be compared to the scale factor? Would it be the same? Would it be 1/3 again?
Take 1/3 and square it.
We have to take 1/3, so the ratio of the areas. Oops, I'm not on my, I'm something else here, so let's take this back, okay? The ratio of the areas is the square of 1/3. The ratio of the areas is the square of our scale factor, which is 1/3. So 1/3 times 1/3, no calculators needed, it is 1/9. There's our ratio of areas. That rectangle would be 1/9 the size of the first one. 9 of those little ones, because it would get smaller, right? 9 of those smaller ones would fit on top of the original one, is really what this is telling us. So questions? Can we find volume with a rectangle? No, it's two-dimensional. Volume is three-dimensional. Okay, so here's what we're going to find the scale factor. A triangle has an area of 20 inches squared. Every dimension of the triangle is multiplied by a scale factor. They don't tell us what it is. And the new triangle has an area of 180 inches squared. So did this triangle get bigger or smaller?
Bigger.
Bigger. So our scale factor better be greater than 1, right? Okay. What was the scale factor? How do you think we could get this? Do you think you really want to go through all the work of having to set up, draw a picture, and do everything else? And Nikki?
You take 180 inches squared over 20 inches squared.
Yeah, set the area of the new one over the area of the original one and divide it out, and what do we get?
9.
9. That's the ratio of the what?
Scale factor.
No, we just found the ratio of the
Area.
areas. Ratio of areas is 9. Is that the scale factor then?
No.
Because is the scale factor the same as the ratio of areas? Or maybe it should be said this way, is the ratio of the areas the same as the scale factor? No. What is it? The ratio of the areas is the square of the, so we need to know what squared equals 9. 3. The scale factor is 3. The sides were tripled. And the area got 9 times bigger when that happened. Okay, number 16. We gotta keep cruising here. A cylinder has a radius of 3 centimeters and a length of 10 centimeters. Every dimension of the cylinder is multiplied by 3 to form a new cylinder. Is it going to get bigger or smaller? The new cylinder? The dimensions are multiplied by 3. It's going to get bigger, okay. How would the ratio of the volumes compare to the ratio of the corresponding dimensions? Anybody in here starting to think, oh, I don't know if I remember how to find the volume of a cylinder?
Oh, I know.
I'm not sure I've heard it quite yet. What is
It's length times.
No.
It's something with base times height.
It's capital B times little h height, but what is capital B? It's the base of it, and the base of it is a circle.
So
So how do you find the area?
times diameter.
H times.
How do you find the area of a circle?
Radius
No, that's circumference. How do you find the area of a circle?
Pi r squared.
Pi r squared. And then so it's pi r squared h. Maybe she didn't. You know, there's so many ways. So you're pi r squared h. Do we really care? Do we really have to use the formula and find it?
Nope.
No. But I wanted to see if you could give me the formula. the ratio of the volumes compared to the ratio of the corresponding dimensions? Well, we don't know the volumes. How are we going to do something like this? What are we going to do? We know that the scale factor is what?
3.
3. Oh, the scale factor is 3. That's good news. I know that much. I didn't have to work very hard because it says right here. Wonder what I could do. John?
I know.
What?
Because isn't the ratio of the volume, it's volumes, so it'd be cubed. So you take your scale factor and you cube it to get your ratio.
You are so right. So all we have to do is go 3 to the 3rd power, right? The scale factor cubed. The scale factor cubed, and what is that?
27.
27. Didn't have to work very hard at all, did we? The ratio of the volumes is, let's put this is the ratio of the volumes, folks. We didn't even have to find those volumes. But if we had found those volumes, we've gone through all that work because we just like to work. The volume of the bigger one divided by the volume of the smaller one would have been what? 27. Yeah. Okay. You see if you can do the next one. Get it started on your own. You have to find the scale factor this time. I bet you can. Find the scale factor for this cone. What is the ratio of the volumes? 8. Yeah. The ratio of the volumes, put the new volume over the old volume and divide it out and cancel those pi's out and take 288 and divide it by 36 and presto you have 8. That is the ratio of the volumes. They want us to get the scale factor. How are we going to get that? John?
Well, I don't really know how to explain it, but I know what the answer is.
Oh, you do? What is it?
2.
2. Because we're really looking for what cubed is 8. That's what we're looking for. What number cubed? What number cubed is 8? What number times itself 3 times is 8? 2 times 2 times 2. The scale factor is 2. Okay. So, any lingering questions about changing dimensions before we practice a little bit more proportional reasoning? Any questions about changing dimensions? Can you do this on your own now?
Yes.
And do you have to have work to support something, even if it's in words?
Yes.
Yeah? You can't just put down tomorrow 2, then 4, whatever.
6.
Yeah, whatever. Okay, so let's take a look at these where we're going to use proportion models to solve. We're going to use proportional reasoning of similar figures because it says right here that triangle ACD is similar to triangle ABE. Well, ACD happens to be this one right here, doesn't it? If I draw it out there by itself, is that ADC? And then triangle ABE happens to be the one that's on top of that, right there, and that is AEB. So we have similar triangles. What's the base length of this one? X. What's the side length of this one? 12. 4 plus 8, 12. Right? And then what's the base length of this one? 5. And what's the side length? 8. Everybody see where we got those? Because we got to be able to pick those up properly, right? Okay. Well then, the other way we could do it is we could say, okay, well we need to know what side CD is, so we could set up a proportion CD over BE equals. We happen to know side AE and AD, so we could do this. But in reality, we can also, so we're really just, that's what we're gonna do. We're gonna do x over 5, corresponding sides, equals 12 over 8. And show that we're solving that. What do you get for x? We're solving for x. I get 7.5. You too? Okay, so x is 7.5, and those happen to be what? Centimeters. Okay. Okay, set up a proportion to do the next one on your own. Set up a proportion. Pick some corresponding sides because they're similar again. So I would start doing some things like, okay, we know QV, so that corresponds with TS. I really, your calculator's going here, I'm gonna go crazy. Are you kidding me? 6x, 3.6 times 10. What's that? 36. Thank you. 6x divided by 6 is x, and 36 divided by 6 is 6. Our answer is 6 centimeters. Okay. Yeah. Okay, so just a little bit more practice on making sure we set up good relationships, okay? Any questions?